All right, so number 19 in 2002, this is asking us which of the molecules has an R configuration, so the R enantiomer. So I drew one of these examples. This is actually answer A, just to kind of go through how to do R and S again. So the first thing you need to do is to make sure that whatever carbon you're talking about actually is bonded to 4 different things. That's important. So make sure they're bonded to 4 different things. So actually, this isn't even A. This is just we'll just do R and S with this. It's fine. This carbon right here is bonded to a hydrogen, a nitrogen, carbon, another carbon, but these 2 carbons are different, so it's actually bonded to 4 different things, excuse me, 4 different things. Then we have to do is rank them. So we have to rank those things, those Kahn-Ingold Prelog rules, you remember? And that's based on atomic number first, right? And it's all about the high card. So it's not about overall who has the highest or total atomic number. It's if you have something with, right, an iodine, that's going to beat a lot of things, right? So it's all about high card. So if we rank, the hydrogen is probably the easiest thing to know for sure. This is ranked 4. What will be ranked the highest? So we have a nitrogen, a carbon, and a carbon. So the nitrogen is going to be ranked the highest. I always like to do the top 2 things first. So that's 1, that's 4. Then we have to rank 2 carbons. This carbon is bonded to 2 hydrogens and a carbon, so its top card is a carbon. This carbon's top card is an oxygen, so this wins. So this would be 2, and this would be 3. Now we need to visualize, and we need to see if something rotates clockwise, that is R. If something rotates to the left, that is S. And when I say rotate, you need to have the lowest priority group in the back. All right, that's one way to look at it. So this is kind of set up nice for us because the H is the lowest priority and that's pointed away from us. So you go 1, 2, 3, that's rotating to the left. This is actually an L configuration. So this one is not, sorry, S. I'm thinking of biology stuff. It's S. It's L in the other term. It's S. Sinister. Rotating to the left. Sinister. So the hard part is 2 things. You got to rank it correctly. If you don't do that, you're going to be in trouble. And then if it rotates counterclockwise, it's S. If it rotates clockwise, it's R. And you got to get that lowest priority group going away from you. I can bring model kits if you want them. The answer to this one is B as well. So 23 in 2002. The question asks is which substrate is most reactive in an SN1 reaction? So what this is really asking is a couple things. First of all, do you know what an SN1 reaction is? And you have to kind of know that. And the other thing is asking you, do you understand carbocation stability and the ways to stabilize carbocations and hybridization for that matter too? So what they don't want you to do is this, is to take all of these, A, B, C, and D. What they don't want you to do is to draw out the carbocation that would form for each of these. Because once you do that, it'll be very clear what the answer is. Right? So if you just look at this, maybe you could figure it out as you're looking at this, but the thing I would do is have these and then draw in, after the first step, right, when you form a carbocation, what's it going to look like? So for this one, electrons move away, right? Because SN1, the leaving group just leaves, right? So take 5 seconds to draw the products of those. So after having drawn out the products, or at least after the first step of the SN1 reaction, we see they form carbocations, right? SN1, E1 before carbocations. So one of these should, actually only one of them is even logically makes any sense. Right? Once you see it, right, this carbocation can be stabilized how? By the resonance, right? This is the benzylic position. That bromine was in the benzylic position. So it can be stabilized by resonance. This carbon is an sp2 hybridized carbon. Are sp2 hybridized carbons going to have a carbocation? No. This one would make a primary carbocation. Do you ever make primary carbocations? Nope. Again, sp2 hybridized carbocation. Can this be stabilized by resonance? This is what they're trying to get you, right? Some people think this can be stabilized by resonance. It can't, right? Because there's an empty orbital there. It's perpendicular to the p orbital system. So the answer is A. But they really write the trick. They wanted you had to write out the product. That was the key. A lot of times they do that with acid-base chemistry too. Write out products. Don't just look at it, write it out. Yeah. And we're back. So let's look at what can happen for each of these individually. So for A, right, what's going to happen here? So we have an O minus. It's just going to take that hydrogen. This is going to be an acid-base reaction, right? This is a base. There's a reactive hydrogen. This is going to be an acid-base reaction. So this is just going to deprotonate that and give you a phenol. B, what kind of reaction is B going to do? So this A does acid-base. B is going to do what kind of reaction? SN2, and give you this product. So that works. That's a possibility. What about C? What would C do? C, this could attack. It can't do SN2, but it could do a nucleophilic aromatic substitution. It's not tertiary. It's sp2 hybridized, but you could do a nucleophilic aromatic substitution where this adds in, electrons come up and then electrons come down and kick out the bromine. That's possible. It's not as likely as B. B is your best answer. D, the reagents just aren't reactive enough. There's no charges. You can think of it that way, right? So it's not going to be that reactive. So the best answer here is B, the SN2. Okay, 29, 2004. This is this has to do with substituting benzene rings. This is like diazonium kind of salt type stuff. So what happens here essentially is the NO2, when there's HCl and iron catalyst around, the NO2 gets turned into NH2. It gets reduced. So NO2 gets reduced to NH2. So then there'd be this step, there'd be NH2 there. Then you add an NO2, NHCl. What that does, that turns the NH2 into an azide. So we start out with, we go from this one to there, and then we turn this into this diazonium salt type deal. And then what happens is the copper bromide comes in and actually does that nucleophilic aromatic substitution where the bromine attacks the carbon. It's not SN2. The pi bond comes up. So you do an addition, negative charge bounces back down, kicks out the N2. So that looks like it attacks, electrons bounce up, you form a tetrahedral intermediate, and then Then you look at what's the best leaving group, or if the N2 leaves, N2 of course is a gas and it's never coming back, and that gets you to the final product where the bromine has been substituted, on here. That's a nucleophilic aromatic substitution. So it's the opposite of electrophilic aromatic substitution. Now, electrophilic aromatic substitution, the benzene ring's the nucleophile. In nucleophilic aromatic substitution, the benzene ring's the electrophile. So the answer for this one is D. Okay, so number 21 from 2002, and it's saying, what is the rate expression for this reaction? So it looks like you have ethyl bromide and methylamine reacting in a polar aprotic solvent. Okay. How to approach this problem? So I guess, what were the two answers you were thinking of? Did you narrow it down to two answers? No. All right. So one of the right. So this is hard because there's no charges. So it's not. You can't immediately say SN1, SN2, or E2, E1. Right. There's no like negative charge, so you know it's going to be right. There's no negative charge, so you know it's not going to form a carbocation. I don't think you're going to form a carbocation because that's a primary alkyl halide, right? So it's not E1 or SN1. So that leaves E2 or SN2. And quite frankly, it doesn't matter which one it is, because if you remember E2 and SN2, hence the name 2, meaning bimolecular, right, means it involves two reactants in the species, right? SN2, it would involve, if we did this as an SN2 reaction, this would be the nitrogen would be the nucleophile, that carbon would be the electrophile, but they'd both be involved in the rate determining step, the only step. If it was E2, this would be the base, and the hydrogen would be here, right? But you still need both things in the rate, right? So both things matter. So the answer here is A, because it involves both reagents. So rate equals K times the concentration of the alkyl halide and the concentration of the amine, the nucleophile or base.
If this wasn't, let's just say if this wasn't SN1, is it the concentration of the nucleophile?
So if it was an SN1, so we hopefully got this as A. I have to add something. And kind of ignore the solvent type deal, even though, whatever. If all of a sudden I made that a tertiary alkyl halide, and I said, now, right, we're in a polar protic solvent, not a polar aprotic solvent, what would the rate depend upon? In that case, the rate only depends on the alkyl halide. So for E1 or SN1, the rate is only determined by the concentration of the alkyl halide. The nucleophile doesn't matter. E1, SN1, it's all about the concentration of the alkyl halide. Good questions.
So don't worry about the solvent.
Solvent has nothing to do with well, it does as in terms of affecting the concentration, but it's not part of the actual reaction. Yeah, they try to throw that D, they do a squared thing on you. No second order that way. No, nothing complicated like that. So taking a look at number 51 in 2002, it's about radical reactions. So it's MBS, bromination reaction. So I didn't draw MBS, but MBS is a way to get allylic radicals. So I should draw in the allylic hydrogens. Right? The allylic, of course, meaning adjacent to the pi bond. So what it's going to do is create an allylic radical. And again, you're not required to know the mechanism for this at this point. So let's just skip that step for right now and assume we get to this point with the allylic radical. And you have some Br dot also floating around. So those can come together. That's one potential thing with these two would come together. And we'd get the bromine just added to that allylic position. That'd be one product. And normally we'd say an allyl piece like this 3-carbon piece is symmetrical, but it's not in this case because we have Ds. We have deuteriums replacing the hydrogens. So it is different. These carbons are technically different now. So what also can happen here, once you make this allylic radical, this radical can do resonance. So we do some carbon numbering here. 1, 2, 3. Draw that resonance, single fishhook arrows. That resonance structure would look now like this, with the deuterium still on carbon 1. Br dot is still floating around. So those two things come together. So you could also get the original product I have drawn plus the bromine could also be on carbon, as I have labeled carbon 1. 1, 2, 3, 3, 2, 1. So those would be the two products that are possible in this case. So what are they asking you? All right, you need to know, what did NBS do? You need to know something about it formed an allylic radical. And then they wanted to see, did you know how to do resonance structures again? Or radical resonance structures.
I mean, even if, for just this question, you just knew that NBS had an allylic bromine. Only one of the answers.
Right, so good test taking skills. So if you get to the point where, okay, I know it adds allylic, let's look at the answers. If only one of them actually adds in the allylic position, that's a pretty good giveaway. Yeah, so the right answer is B, and the other answers are kind of messing with you, trying to have the deuteriums move around, which they don't.
For 56.
So 56 in 2002 is asking which reagent will best accomplish this transformation. So just reviewing your alkyne chemistry, right, or alkene chemistry, ways to get rid of pi bonds by adding hydrogen, right? Classic way, H2, palladium on carbon, or platinum, right? So there's just kind of H2, and then it's usually PT or palladium, and that makes all the pi bonds go away. That adds hydrogens all the way, makes all the pi bonds go away. There's another one called H2, and it's Lindlar's catalyst, and that stops, but it's also, you see the actual thing is called palladium and barium sulfate and quinoline. That is Lindlar's catalyst, and that'll stop. And Lindlar's only works for alkynes. That'll make an alkyne stop at an alkene and make it stop at a cis alkene. It'll add H's on the same side. So it's that syn addition. But it turns an alkyne to an alkene. And it's a syn addition, so you get the cis alkene. But what if you want a trans alkene? Then it's Na, NH3. That sodium, that sea of electrons one. Sodium or lithium, you get a sea of electrons. And that gives you a anti-addition, which gives you trans alkenes. So that's these last two. This works with alkenes or alkynes and makes them go to alkanes. These last two are both for alkynes. H2 in Lindlar's turns an alkyne to an alkene into a cis alkene because it has a syn addition. Sodium metal in NH3, liquid NH3, gives you an anti-addition, gives you a trans alkene. Alkyne to trans alkene. So the answer for 56 is D. Number 53 in 2002. Which reacts fastest in an E1 reaction? So it's very similar to the first question we had. What they don't want you to do is draw out the first step of an E1 reaction. The first step of an E1 reaction is what? The formation of a carbocation. So I'm not going to do that here because I just said you should. So there's two things at play here, though. They've mixed things up a little bit. That other one, they only had bromine, so they had the same leaving group. They just put it on different hybridization state carbons in different positions. Here they're doubling, they're making, there's another layer of complexity. They're also looking at different substitutions, right? Primary, secondary, tertiary carbons, but they're also changing the leaving groups on you too. So there's two factors going into play here. So one thing you want to think about for sure though, the most important thing to think about is primary, secondary, tertiary, the stabilization of the carbocation. That's the more important thing than the leaving group. The more important factor is stabilization of the carbocation. So the first thing you want to do is find the most substituted thing. All right? So that would be C and D are the most substituted. Yes, iodine is a good leaving group, but it doesn't matter if it's a great leaving group if it's going to form a primary carbocation. It doesn't matter. Bromine's a good leaving group too, but that's only going to form a secondary carbocation. These are both going to form tertiary, so it doesn't matter. So now we're just comparing these two. So they're both going to form tertiary carbocations, and the only difference is iodine versus chlorine. Look at your periodic table. The big one wants to go. I could do the iodine sloshing dance for you, right? I did it today for the 251 kids, right? They're all kids, right? So the iodine is a better leaving group because it can stabilize its negative charge better, right? Because it's larger and it can spread that charge out. Also, technically, this is a more reactive bond, right? There's less orbital overlap here between an iodine, which is very large, and a carbon, and a chlorine that's closer in size to the carbon. So the answer is C.
So you want to create a more reactive bond?
Yep. We want to have one that has a more reactive bond, but then also in this case it also forms a more stable product, a more stable carbocation. So number 54 in 2002, it asks you which conditions are most likely to produce the products shown. So what you need to look at before you look at the answers is probably just look at this and say, okay, what happened? So this is alkene chemistry, right? It involves an alkene, and it looks like they added 2 OHs. And what are these relationships to these? What are these two things to each other? What's their relationship to each other? They're enantiomers. So it forms a mixture of enantiomers, whatever this reaction is, and these OHs on the single molecule. What's the relationship to each other? They're same side. They're syn. So whatever it is, you're going to make enantiomers. And it has to be a syn addition. And you're adding how many OHs? 2 of them. Okay. So let's look at the reagents. So they have, for A, they have osmium tetroxide. That's the reagent that matters, of import. The other one they have MCPBA, which is this. They show the molecule. They have O3, so this is A, this is B, C, D, and D is B2H6 and a bunch of other stuff. And there's other stuff with all these reactions, but the important part is this part for all these answers. And a lot of this is you just kind of got to know. Osmium tetroxide gives you syn diols. This is a syn diol. A is the answer. Maybe you've never seen osmium tetroxide. I know you've seen O3. O3 turns an alkene into 2 ketones, so you know that's not the right answer. Boron, adds is an anti-Markovnikov, but adds how many? Just 1 OH. So that can't be it either. MCPBA does an epoxidation. I might need to look more into that. It does an epoxidation. What were the other reagents in that MCPBA thing? Then they had, so that was step 1. Step 2 was NaOH. If you have an epoxide and you add something in, those things end up being, you can get a diol from an epoxide, but those 2 things end up being trans. Epoxides will give you trans products. So osmium tetroxide gives you that syn diol. That's the answer. So a lot of the times is maybe you didn't know this, but you should have known these other ones. So if you convince yourself it's not those, then it has to be that, or at least narrow it down to 2. So yeah, MCPBA makes an epoxide, right? Right, and then that OH minus is going to have to attack from the backside. So it's going to end up being a trans diol, not a syn. Right, 52 in 2002. It's an ozonolysis reaction. It's asking you what is the product of this reaction. what's the starting material? It gives you the product. First thing you gotta do here is number your carbons. You gotta number your carbons. 1, 2, 3, 4, 5, 6. So 6 carbon piece. So whatever molecule this came from, the starting material, this also had 6 carbons. Notice there's only one thing. So what you do is you attach carbon 2 and carbon 6 used to be bonded together. They used to be bonded together. Right? Because that's where the alkene got clipped. So if I do that, I can make it ugly. Let's make it ugly. 2, 6. 2 is bonded to 1, which is bonded to 3. 1, 3, 4, 5, 6. So it looks like we should have a 5-membered ring, right? So you could have narrowed it down probably to A and D right away. The correct answer is D, but number your carbons. Dead giveaway. Number your carbons.
B and C would have made separate.
B and C would have made separate, right? B and C would have made 2 pieces, and actually C would have made 3. Right, taking a look at 57 in 2002, the first step is going to be a Friedel-Crafts acylation. So it's a way to, the nucleophile is the ring, so it's like an electrophilic aromatic substitution. So the first step, you would have added that. The zinc, what the zinc does, the zinc and HCl does a reduction. It does a reduction of the ketone all the way down to the benzylic ketone, all the way down to the alkane. And then Br2 in light does a lilic, or benzylic in this case, bromination. And I believe the product would be that. Yep, so that would be the sequence. Most things kind of got, hopefully you knew bromine added, and A and B in this. Bromine is adding to an sp2 hybridized carbon, which that you don't know how to do that. You've never seen a way how to do that, so you could probably eliminate A and B right off the bat, and you're kind of stuck with C and D, and hopefully you knew something about the zinc is the kind of the key to the reducing thing, the benzylic ketone to the alkane.